What are we doing today? Um, so I want to go ahead with the quantum computer aided design thing because I think that kind of was one of the roads toward that I really wanted to follow towards falling in love with variational quantum algorithms and learning more about variational quantum algorithms. And if I remember well, I did two sessions. One was basically just gonna even I should even have I think a didn't I have a list of to dos? I think I had a list of to dos, which should be. Let me take that out of the screen for a second. Should be in the workspace. Yeah, here it is. So, oh yeah, here we go. Okay, so understand VQD was done. Okay, but that was like alpha. There's some sort of alpha QPE and alpha VQE involved in there. It's like that I also wanted to explore. I wanted to understand the XX Ising coupling gate, the MS gate. Oh yeah, what is the advantage of using MS gate versus the CZ gate? Kind of that connects as well with a bit of my previous video about entanglement and stuff like that, right? Like, is this entanglement all that we need? And I wanted to add something because I also want to dive uh, into cost functions a bit more and concretely understand are they called Barren Plateaus? So I was taking a look. I came back to the tweet to the reply by Marco where he talks through them sort of the stuff that you have to keep in mind when you design a cost function, and the one is it's got to be trainable, so you got to make sure that you can avoid certain known scalability issues like Barren plateaus. So I want to Google that. I mean, I don't know if I'm just going to do that. I think it feels like there's so many things to do that I really don't have any specific sequence of events that I wanted to follow. And in particular, we're talking about these two papers. Those were the I don't know what's the VQT VQD. So what was that? Yeah, this is the paper. So this is where this is explained. The actual algorithm, right? Yeah, exactly. So this was the this is the whole thing. And so if I remember well, I think this was about it's iterative. So you start with classical VQE, and then what you're doing is your cost function has actually two components. So one component is the same that you find in VQE, so that's like minimize the expectation. Oh, wait a second. Updates to minimize. Classical adder calculates these. Oh yeah, exactly. So this is the energy. Yeah. So this is the here you have the expectation value. Expectation value, which kind of translates to the energy, and then your cost function is the energy plus like the Hadamard overlap. So basically, you want to make sure that the state that you're finding next is orthogonal to the one that you've already that you have already found. So you're now like you're looking for the energy of like the lambda k, like sub k, assuming you found like sub I, or I don't know which whatever this is. So exactly. So, but I'm kind of thinking about like, okay, so how do you and here this kind of supposed to work, right? Like, but I wanted to try and understand a bit more. I mean, there's so much that I can dive into, really. For example, I would love to understand how can I know intuitively that a cost function is going to work and it's not going to kind of have scalability issues, or what's the type of work that it's required to actually prove that there's no scalability issues. And because that's intuitively kind of makes sense, right? Like, but my intuition failed when I was doing VQLS because I didn't kind of think about the fact that I cannot just sum the overlaps and expect that for that particular algorithm that's going to give me something that is meaningful. Nevertheless, here you have a sum of two terms, right? Like of an energy and mm, and the overlap in here. So this is kind of my current thought process. Because alpha QPE and alpha VQE, I mean, at some point I want to recap QPE, quantum phase estimation, because I feel like it's been a while without touching it, and then I can use that to touch on alpha QPE. But let's dive into this a little bit, even if it's a shorter video. I don't know. We'll see. I kind of feel like, what do I want to do? So there's definitely okay. So this whole thing is like this is part of the core paper, right? Like the whole thing of understanding the design of the answers for the dynamic part and the static part, as in like that's how you design a quantum computer and that's what you want to do. That's the whole point of the actual paper that took me into these from Alan's group. But then there's the concept of okay, so why are these gates a north, right? And I get it. I know that this is the gate used because it's kind of native in an ion trap computer, I think. So it could as well just be something else. But it's like, is all entanglement the same, right? It's the same kind of question that I'm asking about, like in the other series or in the other video that I did the last time. But let's try to dive into this. It seems like it's sort of the step that I hope to be able to just backtrack to this point and not just uncover more points to go deeper into. Let's just start simple, like simple. Let's just Google this. What a Barren Plateaus? Because I have absolutely no idea. I have a an intuitive understanding of machine learning and stuff like that, but I'm not I'm by far not an expert. Okay, so it's interesting because this pops up as a first result already. Barren Plateaus in quantum neural network training landscapes. Okay, so this seems to be something that is in quantum neural networks, cost function, Barren Plateaus, tensor. Okay, so there's something from TensorFlow Quantum. But why is it everything popping up like in relation to quantum stuff? Like, isn't there like a Wikipedia page which is kind of agnostic to Wikipedia to all these? Barren vegetation, or machine learning. Is it something that's like is this something that is really seems to be quantum like? Okay, let's see what is these. Oh, so there's even. Oh, nice. Okay. Here we go. There's some stuff I've wanted to use Colab for a while. I gave it a try, but like it didn't seem to really work well. Or I just was not. I'm not. No, it's not that it's not working well. It's that I have no idea how to work with it. So. Oh, but look, that's actually part of the tutorials. I did the first one, so everything goes back in circles. How do I do this? Yeah, so I think I'm gonna do this. I feel like I want to try to understand what are these. I hope I don't really have to go through all, or I'm not expected to go through the other ones. But so in this example, we'll explore the result of McLean 2019 that says not just any quantum neural network structure will do well when it comes to learning. In particular, you will see that a certain large family of random quantum circuits do not serve as good quantum neural networks because they have gradients that vanish almost anywhere. In this example, you won't be training any model for a specific learning problem, but instead focusing on the simple problem of understanding the behaviors of gradients. I already like that. The previous tutorial is about calculating gradients, though, so I don't know if I should do these. This tutorial explores gradient calculation algorithms for the expectation values of quantum circuits. That is definitely something worth doing as well. Maybe I should start here. Gradient values. Advanced usage. It's like I might not be able to follow everything that I. Let's see. Let's do it backwards. Sometimes it just helps. So let's start here. How does this work? So do I actually have to? Is it the same? Yeah, it seems like it's similar to Jupyter Notebook. So I click these, and this installs TensorFlow. Install TensorFlow Quantum. And then what are we doing? So while this is going on, so we import TensorFlow Quantum, Circ, SymPy, NumPy. What is SymPy? I forgot. Oh, just symbolic mathematics. Okay. Visualization tools, and okay, so we're initializing random somehow. Yeah. This is installing. It can take a while. Summary. So random quantum circuits with many blocks that look like these. So those are Y rotations. And then RP, what is these? It's a random Pauli operation. Okay. So it's a random Pauli operation. Okay. And this is just a parameter. Okay, but that's not parameterized, as in like that's a fixed angle. And then you've got like controls like gates, which kind of give you the entanglement. Where if fx is defined as the expectation value with regards to ZA, for any qubits A and B, and there's a problem that f prime, like as a mean very close to 0 and that's not very much, you'll see this below. So that's the summary. I don't understand that. Okay, so the first is generating random circuits. Can I just... Is this done? Restart the runtime. Yeah. I might end up doing two things at once. Let's see what I do here. Preliminary. Let's make the notion of a grading calculation for quantum circuits a little more concrete. Suppose that you have a parameterized circuit like this one. Looking at the operator, you know that. What? Okay, back here. So is this working now? Yeah, I think I probably don't need to. Just to read that, I don't need to go through these. I'll probably go through these if I want to just play and explore with some of the cells. It'll be faster if I just read these, and then I can do another session, maybe playing with it, or later at the end of the session, we'll see. So first we generate random circuits. The construction from the paper is straightforward to follow. The following implements a simple function that generates a random quantum circuit, sometimes referred to as a quantum neural network, with a given depth on a set of qubits. So what it does is, this is okay. So this is what we see there above, right? Like, so it rotates for each qubit. The circuit is like an RY rotation on a qubit, and then for a given depth, we are a series of single qubit rotations. So random and random rod, NP random uniform. What? Oh, that's creating a random, a uniform, a uniform distribution to pick a random n, and then what it does is what if the random number is below 2 divided by 3 out of z. If it's 1 divided by 3, then out of y, else out of x. Okay, so it just randomly creates one of those rotations. I guess this random rotations in here. Okay, random rot, like that's the actual rotation. Else symbol, and then add the CZ ladder. Yeah, here. Okay. Generate random QNN. So okay, so click generate random QNN and it generates these, for example. Okay, so so what it generated a symbol for some y, and for some no symbol. If I is not 0 or d is not 0. So for depth, so that, well, basically what this does is for depth, for the first layer and the first qubit, it adds a symbol. That's it. Okay. The authors investigate the gradient of a single parameter. Okay, yeah. So the gradient of a single parameter. That's why this is the only one that's got like these. Let's follow along by placing a SymPy symbol in the circuit where this would be. Since the authors do not analyze the statistics for any other symbols in the circuit, let's replace them with random values now instead of later. Running the circuits, generate a few of the circuits along with an observable to test the claim that the gradients don't vary much. First, generate a batch of random circuits. Choose a random ZZ observable and batch calculate the gradients and variance using TensorFlow Quantum. Yeah, I guess I probably would have to read or do these other tutorial as well. Let's write a helper function that computes the variance of the gradient of a given observable over a batch of circuits. Process batch. So you get the expectation. So set up a simple layer to batch compute the expectation gradients. Prep the inputs as tensors. So circuit tensor. I almost forgot how the whole thing here worked, right? Like you had circuits as tensors actually. Values tensors, yeah. So, and then you use TensorFlow gradient tape to track gradients. TensorFlow gradient tape, what is this? There's a lot of tooling for that. That's pretty cool. Should probably go through the introduction of gradients. That's like that's the normal TensorFlow, right? Wow, there's a lot. I'm such an ignorant. So use a TensorFlow gradient tape to track gradients. GWatch values tensor for whatever this is. So we're calculating the expectation value, then return the variance of gradients across all circuits. So the variance is supposed to tell us how much what's the variance between those different expectation values, right? The standard, is it standard deviation or what is this? Set up and run. So choose the number of random circuits to generate along with their depth and the amount of qubits they should act on. So this is the actual, okay, so we're generating Uh, generate the random circuits and observable for the given n. So that's the observable. Theta var process batch. So for each circuit, we okay. So for n qubits, why do we loop over the qubits? And then we... Okay, yeah, these I don't understand either. Gradient variance in QNNs. Okay, so the more, what is it saying? The more we increase qubits, then the variance of the circuit of the variance decreases. This plot shows that for quantum machine learning problems, you can't simply guess a random QNN ansatz and hope for the best. Some structure must be present in the model circuit in order for gradients to vary to the point where learning can happen. Okay, so what we're doing here is for each random circuit, we're processing the batch, which means we're trying what's the expectation value of that circuit when we shoot it like 200 different values or something like this, and how these vary, right? Like so, and if the variance is low, it means it's bad because it means that the gradient does not really change a lot, and so it does not move a lot, and so it's difficult to actually find any. It might not be useful, right? Because you can get stacked quickly. Whereas if there's big variance, it means that there's big jams. So it means that they can use gradient-based optimization techniques, because then at least it's going to take you somewhere, right? Okay. An interesting heuristic by Grund allows one to start very close to random, but not quite, using the same circuits as McLean et al. The authors propose a different initialization technique for the classical control parameters to avoid Barren plateaus. But can someone tell me what Barren plateaus are? Are they just like the function plateaus and and that's it? Or the initialization technique starts some layers with total random control parameters. But in the layers immediately following, choose parameter such that the initial transformation made by the first few layers is undone. The authors call this an identity block. The advantage of this heuristic is that by changing just a single parameter, all other blocks outside the current block will remain the identity, and the gradient signal comes through much stronger than before. What? This allows users to pick and choose which variables and blocks to modify to get a stronger gradient signal. This heuristic does not prevent the user from falling into a Barren plateau during the training phase and restricts a fully simultaneous update. It just guarantees that you can start outside of a plateau. Okay. The identity block. Maybe explain somewhere else. So that's the actual paper, probably. That's probably the actual paper. Oh, there's a quick recap of the Barren plateau problem. Okay, I can go through this. Okay, but let me read that again. So what's the point? So um, propose a different initialization technique for the classical control parameters to avoid parameters. The initialization technique starts some layers with total random control parameters. But in the layers immediately following, choose parameters such that the initial transformation made by the first few layers is undone. The advantage of this heuristic is that by changing just a single parameter, all other blocks outside of the current block will remain the identity, and the gradient signal comes through much stronger than before. This allows you to pick and choose which variables and blocks to modify. Okay, so what you're doing is okay, so you make layers just cancel each other, so you can pick which parameter works better, right? So you start the testing with one parameter and then you tweak it and you can see how the gradient for that parameter. Okay, the identity block. Okay, I don't know. I don't know if I got it right. A new QNN construction. Now construct a function that generates identity blocks. Okay, let's see. So we're actually gonna do that. Okay. So I see here these and minus, right? Okay, that's actually uncompute. Okay, so that entire block, I see these. So here you have like these are rotations. Then you have the ladders here, the ladder in here, and so this is the uncomputed ladder, and then there's the rotations. Yeah. Oh, that doesn't move. Sorry. uh, and here you have the rotations. So what this is, okay. So what this is doing is just uncomputing the entire layer. Damn it. But how is it gonna? Okay. So here we've done it, but then this layer is. Okay, so this is done just. Now it happens again. Okay. So it just happens, it's just done in some of the layers. Why? Now construct a function to generate identity blocks. This implementation is slightly different than the one from the paper. For now, look at the behavior of the gradient of a single parameter so it's consistent with McLean et al. So some simplifications can be made. To generate an identity block and train the model, generally you need the transpose. Okay, and not this. Initially, theta 1a and theta 1b are the same angles, but they are learned independently. Otherwise, you will always get the identity even after training. The choice for the, I don't understand that. The choice for the number of identity blocks is empirical. The deeper the block, the smaller the variance in the middle of the block. Oh my god. Okay, so even this is even like it just feels so much like trial and error. Like, but at the start and at the end of the block, the variance of the parameter gradient should be large. Why? Why is that? The deeper the block, the smaller the variance in the middle of the block. But at the start and the end of the... This is like, they just dropped this jewel in here and I'm like, what? Why? How do you even know that? It's okay, empirical. So this is, and so what this does is generate initial block with a symbol, generate dagger of initial block without symbol. Oh, this is this. Okay, so the so this is the one without the symbol. And then what is that 1.5 coming from? So this is like, okay, so let me, so the first block starts here and ends like, it sucks because this moves and ends here. Yeah, and then starts the next one with like the 1.5 thingy, 1.15, and then it's okay. So these are two identity blocks in here. Two identity blocks. Okay, but then the only thing you do is the one that has the parameter you're playing with. That parameter is not included in the uncomputation, and so that's not an identity block then, because it's not fully uncomputing that. But how is that? So dagger of initial block without the symbol. And then for D in range, prep and U circuit. Remove the state prep component. What is the state prep component? Oh, the state preparation. So this is the initial, this this is so hacky, this part, like RY, okay. It's so hacky just to use the same. So the idea is you use the random key to generate the layers. Okay. What was the other one doing? Circuits. So here we're using that same. That's so hacky. Okay, but you're using the same function to generate different portions of the, like different layers, and then we're adding these this gate or layer, and then we're adding the dagger version of it. Okay, got it. Comparison. Here you can see that the heuristic does help to keep the variance of the gradient from vanishing as quickly. But wait a second, what are we really doing in here? So this is, when we increase the number of qubits, right? That's because you're uncomputing. You're uncomputing everything else. How does this help? How does this help with anything, though? That's it. Ah. Hmm. I'm not sure I grasp the idea. Nobody seems to tell me what a Barren plateau is, though. Let's take a look. So we recapitulate the original Barren plateau problem and its generalization. Details of the derivation can be found in Appendix A. In the appendix, a parameterized quantum circuit can be described by a sequence of unitary operations that we know, where this is basically okay. Whatever it's a real value parameter is the Hermitian operator, is the fixed unitary. The objective function of a rational problem can be defined as the expectation. Where H is the Hermitian operator representing the observable of interest. The partial derivatives take the form. Okay, that's out of my current understanding. Hard distribution at the second moment. Two designs expect number of samples required to estimate is exponential in the system size. In the expected number of samples required to estimate equation 3 is exponential in system size. So that's the Barren plateau, or no? At the appendix, we re-derive the result of reference 7 for the more general Barren plateau problem. Concretely, it is shown that the gradient in a direction z in the tangent space of the unitary group vanishes in expectation. So, noting that the direction always takes the form for some fixed Hermitian matrix M, it is further shown that the variance becomes exponentially small in the number of qubits. Okay, so this is the definition of the Barren plateau. So basically, the more qubits you have, the less the expectation value varies, and that's an interesting thing. This leads us to believe that the choice of parameterization for quantum circuits is a highly non-trivial task that can determine the success of the rational algorithm. In the next section, we describe a method which resolves the Barren plateau problem for practical purposes. In section 4, we give numerical evidence of two different use cases. Initializing a circuit as a sequence of blocks of identity operators. Intuitively, when I see the word, I'm like, okay, that's not going to be intuitive. Intuitively, the initialization strategy is as follows. We randomly select some of the initial parameter values and choose the remaining values in such a way that the result is a fixed unitary matrix, a deterministic outcome such as the identity. Additionally, we initially ensure that when taking the gradient with respect to any parameter, most of the circuit evaluates to the identity, which restricts its effective depth. Yeah, true. But how can you do that? Like, isn't that somehow? I'm missing some, because that's so they're basically saying what I was kind of thinking, that I mean, what's the point in doing this if you're just canceling out everything? It's like, really, what's the point? Because you're just calculating the gradient of a okay, because all you care is the gradient of a particular parameter, so you don't really care what the other parameters are doing. It's like if you think of them as dimensions, you can do that. Like they're somehow not going to be. That's so much not intuitive. I always thought. I mean, you've got multiple parameters, and if you've got multiple parameters, what is the sense? Yeah, you can just analyze always. Like if I imagine a three-dimensional function, you can always kind of analyze the gradient of one of the dimensions, right? So this means you just project that and just, I guess, just do that, right? Yeah. Okay. This initialization strategy is optimized in order to obtain a non-zero gradient for most parameters in the first iteration. Mm, okay, so the idea is you use these to get a good kickstart, right? So you use this to get a good kickstart. So you just the first step you calculate the gradient of each separate parameter and you ignore the hell out of everything else, and then you just know how to tweak the parameter to then go ahead with your all like the gradient of the whole thing. That's cool. The initialization strategy is optimized in order to obtain non-zero gradient for most parameters in the first iteration. Obviously, this does not a priority guarantee that the algorithm stays far from the Barren Plateau. However, numerical results indicate that this is indeed the case. And so the Barren Plateau is not like the Barren Plateau, I guess, is that you get at some point where there's just the variance doesn't, the expectation value doesn't vary, but it's not your optimal spot, right? However, numerical results indicate that this is indeed the case and that this initialization strategy allows the circuit to be trained efficiently. This gives an immediate advantage compared to previously known methods, which generally do not allow for training any parameters without an exponential cost incurred through the required accuracy. Concluding to ensure that I don't know what those are. U minus U plus do not approach two designs. What are two designs? It's impossible. It's impossible to Google for those things. Okay. What T design? Oh, this. What is T design? That's maybe it. A quantum T design is a probability distribution over either pure quantum states or universe, which can duplicate properties of the probability distribution over the Haar measure. Okay. What? I have no idea what is this. What is a Haar measure? In mathematical analysis, the Haar measure assigns an invariant volume to subsets of locally compact topological groups, consequently defining an integral for functions on those groups. What? This measure was introduced by Alfred Haar. Yeah. Does Haar mean hair? Though a special case for the Lie or Lie groups have been introduced by Adolf Hurwitz invariant integral. Okay, I have no idea what this is. Is the probability is a quantum T design is a probability distribution over either pure quantum states or interpreters, which can duplicate properties of the probability distribution over the Haar measure for polynomials of degree T or less. So to design, it's T equals 2. Complex projective T designs have been studied in quantum information theory as quantum T designs. They are closely related to spherical 2T designs of vectors in the unit sphere. Embedded in C space arise complex projective T designs. Wow. Okay, I'm not going to step into this at the moment, but So we initialize the circuit via m blocks, where each block is of depth L. Depth L is chosen to be sufficiently small so that the blocks are shallow and cannot approach two designs. That bothers me. What are these two designs then? In the following, we'll consider any fixed gate. Okay, whatever. This is then probably semblance of the gradient of two local Paley term decreases exponentially as a function of the number of qubits. That's actually pretty. That's a really interesting. That's a really interesting finding, right? So this means that the more qubits, the less effective your variational. It almost feels like variational algorithms. People say they're like NISQ friendly. It's that they are actually non-NISQ unfriendly. It's like they won't work well in actual big quantum computers. They just work well in small noisy quantum computers. And so, okay, the identity block strategy, basically what this means is just ignore everything else, that it's just pick one parameter, ignore everything else, and figure out what's the gradient of these. So you can kind of have a good jump start. So you basically give it a kick in the right direction, and then you just go ahead with with the actual gradient optimization across all the different parameters at the same time, right? So you're hoping this initial kick kicks you far away from a plateau, or is there anything else to it? Experimental results. This has been more interesting than identity block. It's actually really the n qubits. Wait a second. So this is the variance. What is the difference between A and B? Okay, for the MNIST images, and A is square of Harmar gates for the input state. That's pretty cool. I mean, the effect of this is quite amazing, right? Like it literally. So it literally keeps the variance really high. I mean, in comparison to the random initialization, that's and that would be a cool thing to explore. It's like, what other initialization strategies can you do? I gotta learn. I gotta learn more about these. It just feels like it goes deep down into a big, dark rabbit hole. Yeah, basically. But I'm quite happy. What the hell is this plateau? The plateau. So the plateau is defined by the point where the expectation values don't vary anymore. I mean, that's and again, this is all, I guess, you're using. I mean, using expectation value, to be honest, is a design choice as well, right? So, training a variational quantum eigensolver. In this experiment, we use the empty block strategy to train a variational eigensolver to find ground state energies. We choose a 7-qubit Heisenberg model on a 1D lattice with periodic boundary conditions and in the presence of an magnetic field. Okay, so now they're going to do the random versus the variance of the partial derivatives across 200 trials for a circle initialized using M2 identity blocks and L33 layers per block, and be a random initialized circuit with the same number of layers in total. I don't remember what was the M in here. Oh. Okay, how to read these? Variance of the gradient of a VQE circuit at the start of training across 200 trials for a circuit initialized. So the variance. Okay, so each of the colors are each of the qubits. It's a funny shape though. Um, and so variance go. Okay, so it seems like it's interesting. So it seems like, is this the amount of layers, or is it the variance within each layer? Yeah, that is actually within each layer. So the variance increases. But how? Okay, so how the heck can you calculate the variance of something? Okay, yeah. So you can't do. Hmm, you can't do the identity. How do you calculate that? How do you calculate the variance of the expectation value within one specific layer? Just by placing, I'm guessing. Okay, just place it. Just the parameter is in there, is in the middle. Because I'm getting confused sometimes with the initialization strategy where you just put everything, like cancel everything out with an identity block strategy versus, okay, no, so this is basically saying, no, we're going to kickstart it using the identity block strategy, and then we're going to calculate, okay, and then we're really going to calculate um, the actual variance of that, okay, within layer, like in the middle of the layer. Okay, so these basically what it does is the variance decreases somewhere in here, and it increases in here. But it's still really what bothers me is that I feel I'm just really floating high level, and I don't really quite understand the nuance behind these, right? Like the nuances behind these, as in like saying what that when you're in layer 20, like if the parameter you're calculating the derivative or like the gradient for is in layer 20, that's the type of variance you're going to get. So this means that you're going to get higher variance if you put parameters somewhere in the middle. But what does this mean? What does this imply, intuitively speaking? Does this mean that parameters that are in like sort of mid depth of a circuit have a higher impact on the gradient, and that's just something that is true no matter what? This is what I don't. This is this the fact that this is speaking like this is what is confusing me a little bit. I mean, they do mention this in the TensorFlow quantum tutorial as well, right? Where did they mention this? Something in the middle block, yeah. The deeper block, so the choice of another network is empirical. The deeper the block, the smaller the variance in the middle of the block. I thought it was the opposite, right? Okay. Okay, this is something. So this is something I definitely wanna. So I kind of got a good. I feel I know more. That's actually definitely important. But I really need to deep dive into this. But man, that's gonna be. But I mean, at least I'm kind of bringing a lot of the things together. So also when talking about entanglement, and how does entanglement affect, for example, right? Like how does entanglement affect expectation values and stuff like that? Or in terms of how much entanglement there is, right? Because it seems like by choice, all those ansatz they're just like they just go with like full entanglement, right? So okay, but let me write. Well, I wanted to write something. I wanted to write that. I think I done-ish, right? Like I started. So, but what I definitely want to know is I want to know. I definitely want to know. I forgot. So yeah, what's up? So what's up with variance of expectation values in the middle, beginning, and of a block? That's still something that I really want to clarify. Okay, but the essence, I've got the essence that the concept here is that if you just isolate, if you just forget about everything else, and you kind of cancel out all the other layers by using this identity trick, and you just focus on one parameter alone. But then that gives you a good kickstart because you can calculate the gradient for that parameter, and then that takes you somewhere. And I mean, at least these numerical results verify these. But it doesn't seem so obvious because the point is if your parameter is if you have a really deep block, right? And just focus on one layer. If you have a really deep block, um, and you're doing this uncomputation stuff in here. So here the block is these, and so you're computing the part in the middle. Yeah, I don't know. It's like if you have a really deep block, is this strategy going to work out well? Like, so this is the part that you're playing with, and so this is the one that you leave. So you're uncomputing these by doing the minus versions in here, and then when you move to, I hate that these things stay, of course. And then you basically have these two guys in here, but you don't have that rotation with the theta. That's not in here because then. But wait a second, something is chosen instead. But I don't know if this is just that it's misaligned or I think I don't know. That's picked up. That's picked randomly actually. Yeah, that's picked randomly. So okay, so actually they do. So is that picked randomly? It seems like. I guess so. Where is this? Where is this defined though? Because you have the U and then the U prep U and then U dagger. Oh, okay. So the U dagger it just gives it a random. Okay. So this is basically, I think, the part of the code that generates that, which is basically instead of because it's you just do something random. So you add some random, and then that's effectively you're just doing this, and everything else is cancelled out. That's effective cancelled out, and so that is effective cancelled out. So that, to be honest, you're just calculating these in isolation, right? Like, and the idea is, that this is. It doesn't seem to be. Is there a formal proof, or is it just numerical? A numerical proof that this kind of gives you, or is there a formal proof in here somewhere? Probably, but yeah, the point is that that idea kind of gives you a good kickstart. So that's the takeaway from these. And then apart from the fact that, well, I have a long list ahead of me, but I'm enjoying that. I think I finally, oh yeah, and it's funny. It seems like version algorithms are not only good for, the NISQUE, they're just bad for actual quantum computers because it's so crazy. So the expectation value expectation values variance decreases exponentially with the number of qubits. Yeah, cool. I hope you enjoyed the video. Been a bit longer than I expected, but I enjoyed it as well. So I had a lot of fun. There's definitely a lot of exploring here, and I'm definitely going to play with these and all the other tutorials. And then, because I was planning to do that anyway, so cool. Then stay tuned for more stuff coming soon. Variational stuff, variational love.